All right, welcome everybody. I'm Alex Miller. I'm going to talk today about some Clojure topics. This will probably be the least technical topic of the day, so it's perfect for your post-lunch, just getting back into the afternoon. So who am I? I have been working on the Clojure core team since 2013. I currently work during the day for Nubank, I'm sort of working on open source through Nubank. I have either been the creator or the organizer of lots of different conferences that you may have heard of. And I've been working with Java and the JVM since 1997. Thank you for building a great platform. It has pretty much sustained my entire career. So thank you. And the agenda today is really 4 parts. We're going to talk a little bit about Clojure and just as a baseline. And then we'll talk about the core async library. Talk a little bit about virtual threads and how we're sort of evolving the core async library with those. And then about a new library called Flow. This is kind of got in the door talking about virtual threads here. There's really sort of a bigger story here about building systems out of simpler parts with virtual threads sort of as a tool in the middle there. So Clojure, how many people here have written a program in Clojure? A few. Okay, how many people have heard of Clojure or seen Clojure? Okay, good. I'll take that. So Clojure was created by Rich Hickey, and it came out in 2007. It's a functional programming language, essentially a Lisp, hosted on the JVM. There are also dialects of it that run on JavaScript and on the CLR and on a variety of other things. It uses immutable collections. It's probably a key thing people might have heard of. It features an approach to safe concurrency, so not user-level locking, but mostly relying on immutable values, including immutable collections. And then for managing state, it has a software transactional memory component and also relies a lot on using effectively atomic values, so atoms. Including the STM was kind of an important part of Rich's story about how Clojure works, and he did a talk here called Are We Finished Yet? Here at the JVM Language Summit, probably, I don't know when that was, 2011 or 12, something like that, which was really kind of about that. I think the thing we've learned to report back to you from the future is that you really don't need the STM most of the time. Most Clojure programs don't use the STM at all or use it very, very sparingly. And you can actually store the majority of your state in your program in a small number of atoms. Which is how most Clojure programs are written these days. It's an expressive or a growable language. We have macros and a lot of interesting features for that. And it really focuses on an interactive programming model at the REPL. So you're constantly working at the REPL, evaluating code, and getting feedback immediately. Behind the scenes, we're compiling that code to bytecode and dynamically loading it into a class loader. So we're doing all those same kinds of things you get in Java, but we're just doing it sort of dynamically at the REPL. Most Clojure users are totally unaware of that. So the key Clojure value proposition, and I'm kind of telling you about the language without trying to do a Clojure intro here, but the Clojure value proposition is really to provide this simple set of values, collections, which are also values because they're immutable, and to represent all of your problem, your domain problem, as generic information, not by modeling as classes, but by modeling it mostly as maps and vectors and things like that. And then to write mostly pure functions that manipulate immutable values to immutable values, use a little bit of state where you need, and don't do anything else. And we found that to be a very profitable strategy. There's a lot of big companies using Clojure to run their entire operation. So I work at Nubank. We're the largest fintech in Latin America, 120 million customers. A fairly large company. The whole company is built on Clojure. The system of record primarily is Datomic, which is a database written in Clojure. So we've bet pretty hard on that idea. We've got thousands of Clojure developers writing code this way. So our approach to the JVM, I thought I should cover this since we're here at the JVM Language Summit. The general approach is to embrace the host. So we try to use Java types when possible. We don't like wrap strings or wrap lists or things like that. We try to use all of the basic numeric types and the, that sort of thing. Clojure types implement the appropriate Java interfaces when necessary. Clojure functions implement runnable and callable. Clojure collections implement list and map and all those kinds of things. We really leverage the JVM ecosystem, so we leverage all the work that you are doing in the JDK. Our goal is not to wrap all that and make Clojure versions of that, but to make interop easy and to call those things directly. And we leverage all of obviously the JVM ecosystem, all the libraries and Maven and all of those kinds of things. Our requirements on the JVM has always been sort of kind of the opposite of the JRuby approach, I would say. So JRuby tends to take this very forward approach and try to squeeze every last bit out of all the new features in the JVM, which is awesome. I'm not trying to cast aspersions on that. They're doing awesome stuff there. We've always taken sort of the opposite approach, a very conservative approach. You don't have to specify any special JVM flags. We currently are based on Java 8. That will probably change to Java 17 in the next version. But we've been, supporting an old versions and trying to not force our users to upgrade unless they need to. For us, stability is paramount, and I think Java and the JVM share that goal. It's why doing this work of making new language features is hard, right? To think about how to evolve the language in a way that doesn't break your existing users. We tend to wait for new JVM features to be really well used and optimized before we adopt them. And so we've really only started using Invoke Dynamic within the last year or two, and only in a few places. I think that will probably increase. And I think as we move to a higher JVM version, we'll probably use constant dynamic and hidden classes. And I think there's lots of things that we could utilize. So we're looking forward to using those things. So core async moving forward is a library. It was designed by Rich Hickey, and I'll mention Rich a number of times during this talk. Everything I'm communicating to you is really ideas driven by Rich, and he designed everything that I'm talking about today and implemented a lot of it. He retired from full-time job type work a couple years ago, but is still very actively working on Clojure. I talk to him every week and still coming up with new features and new ideas all the time. And so it's a joy to be able to continue working with him. How do we build and write programs? So the way that we build them is to start with immutable data values, separate processing out into different processes with different jobs. And we need to do several different kinds of jobs. We need to transform data from one thing into another. So functions are a good solution for that. We need to record data. So we tend to focus more on immutable stores, and Datomic is the one that Rich designed, but there are several other ones that people use in Clojure and other tools out there. Things like S3 is another immutable store. We need to remember things, so stateful kinds of things, and this was the sort of Are We There Yet talk that Rich did here many years ago. And we want to decouple the different parts of our program into independent components. And the best way to do that is with queues that allow us to sort of decouple the interfaces between those things. And then we need ways to move and route values between those components. So core async was a library released in 2013. So it's hard to believe because I remember working on it. It was one of the first things I worked on in the Clojure team. And the objectives here were to provide some of these core facilities for Clojure programmers to use. So to provide these facilities for sort of independent threads of activity, communicating via queue-like channels. And we wanted to support the same programming model on both the JVM, which has real threads, and for Clojure script, which runs on JavaScript engines, which are typically not threaded in that way. We wanted to be able to provide back pressure for managing data flow between those components. And we wanted to build upon the sort of the ideas in communicating sequential processes and the derivatives in things like Go. So I'm going to cover just a couple of the key components of it. The queue-like things that we have are channels. Channels have multiple readers, multiple writers. The fundamental operators are obviously put and take. Those have both blocking and parking variants and some constraints about when you can use those. And there's a bunch of different buffer choices. There are provided, unbuffered, fixed size. And then if you have too many events coming through a channel, you need to, if you don't want to handle back pressure, then you need some way to handle the buffer filling up. So dropping and sliding allow you to start dropping values at the beginning or the end of the buffer, which both might be good policies depending on what kind of a system you're doing. If you're getting a string of keyboard events, maybe you don't care about the old ones, you care about the new ones. So there's different options. The values that go on the channel are values, first-class values. Channels themselves are values. So you can pass them around and pass them to functions and things like that. Nil is not allowed. So that's the basic idea there, is that these are our conveyor belts of things, and a nil is an absence of a thing. So we don't put nil on the channel. And that also allows us to use it as a token kind of a thing for different circumstances. There's a little bit of code here, Clojure code at the bottom. So chan here is the Clojure core async function that creates a channel. We're creating it with a fixed size buffer of size 10, and def is creating a var named ch that holds that channel. As you might notice, there's no types, and Clojure is a dynamically typed language, so generally you're not specifying types unless you're doing interop type things. The greater than bang bang is a blocking put operation. You can read the sort of direction of the arrow as the direction of values into or out of the channel. So in this case, the arrow is going into the channel, so it's putting the value 100 into the channel. And then the next call is a blocking take that takes a value out of the channel. It's going to take 100 out. And then close bang is another function to close a channel. So that's just like really intro to the channel API. Kind of the killer feature of this is alts, which basically is like alt and go or select on a socket. It lets you basically specify several channel operations and complete at most one of them. And then there are options for things like priority. There are ways to create timeout channels, so you can use those as well, which I'm not going to cover. And importantly, this is alt is just another function. It's not actually syntax in the language, which is kind of a difference with Go. So in this example, we're creating two different channels here named chan1 and chan2. I'm not passing size, so that's actually creating an unbuffered channel. So it's sort of a rendezvous. Those things are gonna, if you put, it has to wait for a taker to match up to it. Future is a Clojure core function, so it's not a feature of core async, but it just lets you basically execute a body on a background thread, and you get back a future object, a Java-line concurrent future that you can wait on or deref. So I'm pushing this call into the background that says, put a value onto the channel, put 100 onto this channel, do that in the background. It's going to block, so that's why I'm doing it in the background. And then in the current thread, I'm going to alts over two operations. If you just specify a channel, it says, that means I want to take from that channel. But if you specify a vector, that means I want to put a value on that channel. So this alt here is trying to put, is alting over a put and a take, one of which will succeed. In this case, the take from the channel succeeds, and you get back the value that you got and who you got it from. Go blocks. So Go blocks are where things start to get interesting. So we wanted to be able to unmap the thread if it doesn't have work to do. So this might sound familiar, might start to sound like virtual threads. So Go blocks are an execution context. So just like future in the last slide, Go contains a body which will be run somewhere. We're not going to tell you exactly where, on some thread. And when it encounters a parking operation, it's going to basically, if it can complete that parking operation, it will just continue executing. Otherwise, it can actually park and basically unbind from the thread and save that state to be able to run when the parking operation can succeed later on. How do we do that? So we did that in a library, a Clojure library with a macro. And this Go macro actually analyzes the body and emits it into an SSA form. You may have heard about that today. If only there was something useful we could do with that SSA form. So we have the ability to run that on a state machine. The state machine, when it gets to the point where it would execute the parking operation, knows whether or not it can run or not, and then can just save the state of that state machine off. It has, there's some hero programming here. It's basically re-implementing the Clojure analyzer, which is written in Java inside the Clojure compiler. It re-implements that in Clojure, uses another library called Tools Analyzer, which is basically code that will parse. It will parse Clojure code and turn it into an AST form. And so there is some code inside core async that will convert that AST form into SSA form. That was written by Tim Baldridge back in the day. And it basically gives us the ability to analyze the body of this Clojure code and transform it and all this stuff and run it on a thread pool with pausing. Blocking I/O is not allowed because we don't have any way to park out of a blocking operation. At this point, this was written in 2013. So we don't enforce that. There are some tools to actually detect that stuff, but we don't enforce it other than for core async operations themselves. So in this example below, you see that line where we have the Go block. The body of that Go block is taking from a channel and printing. That code is getting translated into SSA form and run on a thread executor. So enter virtual threads. So we now have virtual threads, and I think nothing here is interesting or should be surprising to anybody in this room. But we had new capabilities now for being able to park and unmount from threads in the JVM itself. And so the natural question was, can we use this to our good? And as we started looking at these things, we really looked at the different kinds of things we were doing in core async and like, where could we apply virtual threads? Like we can use them for blocking I/O, which before we couldn't do in Go blocks, we could only do them in real platform threads. Are we going to use them for compute? No, it's probably not a good idea for that. We should use real threads for that, and then we can map them to real platform threads and limit them. It is good for process coordination, channel I/O, and that's what we are already using parking ops for in Go threads and Go blocks. So kind of a key insight that came out of that is there are really three different kinds of workloads. So there's we're creating three new executor pools inside core async for different kinds of workloads. There's I/O, which is where you can do blocking I/O. That's fine. It's obviously a very good match for virtual threads. There's compute, which should never block. It might use to fix a fixed size thread pool, real threads. And then there's mixed, where you're doing a mix of things or we don't know what you're doing. In that case, because you may block, you should probably use, and you may compute, we decided to use real threads for that, platform threads for that. This is an idea that we might also extend back to Clojure. It's currently in core async. The next version of Clojure, we might add some new features into Clojure to let you do like that future call that I had before. We might have a future I/O call that lets you operate a background task, but do it in a pool that's mapped to virtual threads and can block. We've also added a new execution context called I/O thread that explicitly allows us to use our new IO pool of executor pool, and that will be bound to virtual threads when available. So it's sort of like Go, but it also supports blocking IO and continues to do parking channel operations as before. And then Go blocks. So like the interesting thing here is that virtual threads really support a superset of what Go did before. They both support parking on channel operations. For running a Go block on a virtual thread, we really need to map a parking operation into a blocking operation on the JVM, which can then be parked by the JVM itself. But we can do that in both cases. And then virtual threads also support parking on all these other IO operations. But because it's a superset, we can change the existing implementation and not break anybody. You could potentially gain some additional functionality. And for that part, we will encourage people to use the new thing, IO thread, which will be able to have backwards compatibility. If you're already using Go, you can continue using it the way you're using it. So we're going to run those Go blocks in bodies and virtual threads. We're going to stop using the analyzer and the expander. This is a huge simplification. It's a large and complicated duplicate set of code in a different language that has to track all the language changes to Clojure itself. So being able to move off of that is a huge benefit to us from a maintenance point of view. It's also a source of a lot of really subtle problems. And then we'll map the existing parking channel operations when you're doing this into the blocking operations. So we've spent a lot of time this year working on how to do this evolution compatibly with the old code. And so we're trying to do this without making a new, breaking version of the library. This is a library that a lot of Clojure users use. We're trying to make sure that it still runs even if you're not using Java 21. You're going to be restricted in what sorts of things you have available to you. You're not going to be able to get all of the new features and things like that. Most Clojure users are, at this point, running on Java 21 or higher, we believe. We know they're mostly running on Java 17 or higher, but we haven't done our annual survey yet this year. But I suspect most are now running on 21. For users that are upgrading to new JVMs, we want them to get these virtual thread benefits without changing their existing program. So it was really important not to introduce new flags that they had to set or new APIs that they had to call. If they're using Go blocks now, they continue to work. They have the exact same semantics they had before, but they run on virtual threads now. If you want new functionality, like being able to intermingle that with blocking IO calls, you can get that by opting into new execution contexts like IO thread. Doing that is basically a one place. If you're saying, I'm using Go now, but I want to upgrade to this IO thread that has new functionality, it's one place that you can sort of upgrade into that. We wanted to make sure that already compiled Go code, so that's already compiled, done the analyzer, compiled it into the state machine code, that continues to work. So we're continuing to ship the runtime part of the state machine stuff. That stuff is small, so that's nice. And we wanted to give control to sort of enterprise users to control when they switch to these things. So while we want users on new JVMs to get this new functionality, we also want to allow users to avoid that for a while if they need to, until they can properly vet that, test in their staging environments, all that kind of thing. So we did add a property that allows you to target vthreads, in which case you say, I really want to use this. And if you compile code like that and you try to run it on a runtime without it, it will say, I can't do that anymore. You told me you wanted to target vthreads, and they're not here. So, but you can also say avoid. And so that means I'm going to basically, you should continue compiling the old way for now. And you're basically, the emitted code is basically the same as it was in that case. I work at Nubank. We have thousands of services running in production, running our entire business. Many of them are using core async. Many of them don't know they're using core async because they're using it 5 libraries deep or something like that. So We need some way to test this stuff, safely before we can sort of flip the switch and move over. I have just started to do a little bit of testing with this. This is a test, initial test that I wrote. It just creates a chain of Go blocks, n long. So the x-axis down there is the number of Go blocks. And then it just pushes 1,000 messages into the front and waits for the ball to come out the back. So it's not doing any work. It's really just coordination and switching time. And this is a log-log graph. So you should read the linear, the line in a log-log graph is a bad thing. And then, so the blue is the before and the red is the after. Lower here is the total time, so that's good. This is just an initial test. There's lots more kinds of tests to run still, but that was very encouraging. I will say that as I also watched the heap for these two, they behave very differently. I'm not saying that it's good or bad. I'm still trying to understand all the ramifications of that. We're obviously storing all these vthread stacks on the heap. So that is increasing, or it's different. We were before storing all the Go block stuff on the heap. So in both cases, we're storing stuff on the heap. I don't really have a good sense yet of how that plays out and how it will affect real services in production. I'm going to be diving into that with a couple teams over the next couple months at Nubank. All right, so I wanted to move on to continue this story. So we have sort of had this story of Clojure, which is really based on using immutable collections and immutable values, writing pure functions, and then core async, which allows us to then separate those out into components, communicate via channels. So Flow is a new addition to the core async library that we released this year. And so this is sort of a little it's real code, but pseudocode of how you might write a core async loop to sit there and just take in messages on a channel, transform them, emit them on some output thing. There's a lot of different stuff baked into this code. So it bakes in, and I wouldn't even really try to read all this and understand the code necessarily, but the outer parts are really pointing out places where there are policy decisions being made here in line in the code. So there's nothing here that's really handling life cycle of those threads very well. There's nothing, the caller here is handling all of the wiring explicitly. The topology of the overall set of core async Go blocks is really just emergent as you sort of connect. Whoever is responsible for connecting them all together is handling all that. There's not really any error handling in this code right now. There are a bunch of techniques people use for handling core async error handling. And there's libraries for that sort of thing. This is not doing any of that stuff, but the code is sort of interleaving the pure parts of it. The actual pure part of this is the transform. Transform is taking the old state and the new data that we got and returning basically new state and some results that we need to do something with. And it's sort of baked in also the thread policy of like, am I using a thread or a virtual thread or a Go block or whatever? That's all kind of baked in here. So the idea of Flow is that core async has these base constructs, but there's too many concerns and they're still too entwined to put on the user. And the big thesis for a lot of the design work that Rich does is how do we pull these things apart into simpler pieces that we can recombine in different ways. So what we want are functions that are just input to output. So again, just pure functions that take values and return values. We want to map those functions running in a loop on some workload. So when we have these new concepts of workloads for that. And then we want to sort of wire them together with channels, but we don't want to do all that manually. We want to have a little bit more of that done for us. So the Flow model is sort of a strict separation of application logic, those little transform functions, from process topology, from how you execute it, how you communicate, how the life cycle, starting and stopping, pausing and resuming, how you monitor this and see what's happening inside the flow, how you handle errors and report errors, all that kind of stuff. And sort of the three main concepts here are a process, which is just a thread of activity with named input and outputs. They're going to be mapped to channels, but you just give them names, like I'm taking an in, I'm producing, an out. The connection, which just feeds an output to an input, that's going to obviously map to some kind of channel. It's actually can be more complicated than that, how you connect the channels. And then a flow, which really is the resulting directed graph of processes communicating via connections. So that's the model. It's not particularly hard. It looks like your classic directed acyclic graph or whatever. So with processes, your responsibility as a user is to provide a step function, often a pure function, doesn't have to be. It's going to take the process state, which can be arbitrary, and it'll be maintained by your process. You'll take input port messages. So on an input, I got a value, and then you're going to return the modified state and any output messages that I need to put. It's fully testable in isolation because it's just a pure function. So that's easy enough. There's no channels involved in it. And if you create these things with a Clojure var, Clojure vars are reloadable. So the load process does some redirection to go look up the current implementation of the var. So that allows you to, again, implement this stuff with the REPL. You're dynamically changing your code, reloading it as you go. And there's hotkeys for all that stuff in your IDE. So you're modify the code, hit the button, run the thing again. So you're just stay in the flow. No pun intended. So the process, which is provided by Flow, handles basically everything around that. It handles the execution loop, maintaining the state as it goes between those, talking to the input and output channels. It handles all the lifecycle concerns. If your function throws an exception, it catches that, sends it to centralized reporting place. It handles monitoring, so you can ping the process and find out if it's okay. This is an example of a step function, and a step function is actually has 4 different arities. The thing I was just talking about was really the transform arity, which is the bottom one there. So there's, on the left here, there's 4 different arities. A 0 arity, which is describe. So this step function is self-describing. It says, I have a parameter, which takes a predicate. This function is going to evaluate a predicate on its input value and send it to either a true channel or a false channel. So its inputs are one named in. It has 2 outputs, which are T and F, and it's going to run on a compute workload because it's not doing any I/O. The init basically takes arguments coming from the flow and returns the initial state. In this case, it's just going to basically be a map that contains a pred key. State transitions is for start, stop, pause, resume, which doesn't really do anything. And then the transform is basically the part that says, I'm going to take my state, in particular, I'm going to get the predicate out of it. And then I'm getting, on some input channel, I'm getting a value. And I'm going to return the updated state, which isn't changing. This is a pure step function, so it's not changing the state at all. And then I'm going to return the value on either the T or the F channel, depending on whether pred val returns true or false. When you create a flow from this config, you're going to, when you create a flow to use the step fun, you're going to create a set of processes and a set of connections. In this case, we're creating a process named split proc that takes the actual proc function, which this is where we use the var to wrap it into a process. And then we pass the args, which is, I passed the odd function in there. You're to define some connections. I didn't define all the inputs and outputs to this, but you define your other processes there. If you want to test this function, you can test it in isolation. It is just you can call split on, call its transform arity. It's got the pred even, that's its state, and then on the input value you get 10, and the output value you're going to get 10 message on the true channel. So just an example of how you can do all of that. Connections implemented with core.async channels. They have back pressure. We've got all the buffer options I talked about before. Those are all available. There are ways to do multi-routing, so to copy a value across to multiple places. There's some pub sub options. There's lots of different things that are available with channels. Source and sink processes, so the ones on the edges of the graph, can provide the channels to the flow, and that allows you to connect to sort of external inputs or outputs. And that's good, especially if you're connecting to other things. And then flow itself, you provide some config. That was that little map that I passed. That specifies the processes, the connections. Flow then starts all the threads, starts all the workload executors, maps the processes into those executors, wires them together with channels, handles all of that stuff. So the benefits here, the logic is in independent testable pure functions. The topology is centralized and explicit in that config, that flow config, and the structure of the graph is not distributed and emergent from the call chain and threads and queues and all those things that you made. So the summary of all this is there's sort of a shared story here from Clojure to core async to flow, starting with data, focusing on using functions to transform values from one to the other, minimizing your state, separating the threads of execution into different processes, connecting those with queues, channels, and it's all built on the JVM. And so thanks for your stability there and your stewardship, and wouldn't be possible without that. And there's some links at the end. Time for questions? Or?
What was the reasoning behind using a multi-arity function over a protocol for the...
So another member of the core team just recently wrote a post about this. I don't know if I can do it justice in an answer in a Q&A. So Mike Fogus just wrote a post about this recently, but it's something we did consider. We did actually do a whole design sheet about that. And I'm not going to do it justice in an answer. So I will follow up with you on that afterwards. But it allows us to pass it all as one unit. That's a big benefit. But yes, there was definitely trade-offs there between using protocols and we considered all of those things. So yeah.
So obviously, like the that list of reasons why complecting all of the different characteristics the old way was undesirable. What's the relationship between the ideation for flow and the availability of virtual threads? Is this something that absolutely needed virtual threads before it could proceed, was sitting around waiting for years before, waiting for the substrate to be available, or was it just an all lucky coincidence that these came together at the same time?
I think it's one of those cases where the juices were flowing, We sort of came back and revisited a lot of the original design ideas in core async because we had this new tool to use. And so we were thinking about it again a lot. And the ideas in flow really, if you go back and look at some of these old talks, like this Rich Hickey's Language of the System talk, which was from 2011 or 12, something like that, it actually has a section about flow in it, where he uses the word flow there. But those ideas, there's a lot of ideas in that talk that have since turned into libraries and parts of Clojure. So it contained the germs of transit, which is a data format specification, and core async, which didn't exist yet, and flow, and some other things. So Rich had been thinking about these things for a long time. He also, so Rich's background is as an audio engineer, and he's still doing some of that work as a hobby. And so he was working on some MIDI routing things and writing things with core async at the time, and finding that he was writing all this boilerplate, which he could definitely do. He's qualified to do that work. But he was like, we didn't do enough here. We didn't get to the end of this story to really separate out all those concerns for people. And you see that when people who write core async there are a bunch of libraries that people have written around core async, and there's really like we didn't do enough work there to help people fully separate their programs. So we didn't need virtual threads to do that. It's not dependent directly on virtual threads. The workload stuff really came out of our looking at all these things again and thinking about how we could map different workloads to different thread pools. And we're using those inside Flow, but we could have done things in other ways, I think. So.